Hello everybody! Today we're going to cover plate tectonics, which is chapter 2 of your textbook. Okay, so until about the 1960s, scientists thought that continents and ocean basins had a fixed geographic location and that they were very, very old. In the following decades, so in the 60s as they were later 60s and 70s, which is really pretty recent, scientists came to realize that the Earth's continents are not static, but that rather they migrate gradually across the globe. So some of the movements that these blocks are engaged in causes them, for example, to collide against one another, which in turn causes deformation in the crust and creates mountain chains, for example. Also, sometimes these blocks split apart, and as these land masses separate, new ocean basins emerge in between the two blocks that are splitting. At the same time, sometimes other parts of the seafloor plunge into the mantle. So seafloor that is more dense than continental mass will be plunging into the mantle if that is the motion that the specific plate is under. And we'll cover this as we go. So with all of these processes taking place, a new model, which was very different from anything thought of before, arose, giving us an explanation to the Earth's tectonic processes that deform the Earth's crust to create the major structural features that we see, such as mountains, islands, continents, and ocean basins. So the word tectonics comes from tecto, which means to build. So tectonic processes mean the processes that build up the Earth's features. So this scientific revolution started in the early 20th century as a relatively straightforward proposal termed by continental drift. Okay, continental drift. I'll refer to it many times this lecture. But for more than about 50 years, this initial idea of continental drift was rejected, given the evidence that supported this idea. They said the evidence was not sufficient, and that based mostly on features in the southern hemisphere that were the evidence given towards this idea, they couldn't back it up all the way. And the reason that they couldn't back it up all the way was because most of the geologists at the time, most of the scientists came from areas in the northern hemisphere. So evidence that came from the southern hemisphere was a little bit too unfamiliar and foreign for them, so they were less likely to back up that idea. So they went ahead and rejected it for the most part, partly again because of the evidence, and also partly because of the mechanisms that this idea had as a driver. However, after World War II, the newer instrumentation and more researchers that were now experts in geophysics and geochemistry after that, we found new discoveries that were made and that rekindled the interest in the continental drift hypothesis. So by the late 60s, developments were made towards a new encompassing explanation. This new encompassing explanation is what we call today the theory of plate tectonics. So in this lecture that I'm going to do today, we'll cover the initial continental drift hypothesis, the valid evidence that it had, and why the hypothesis was rejected at the time that it was created. And then we'll cover how it led to the theory of plate tectonics based on its accepted evidence. Along with that, we'll also cover the evidence for the theory of plate tectonics, the motions that cause plates to move, or what are the causes for them to move, I should say, and what are some of the methods that we use currently for measuring the plate motion. So we'll cover all of these topics in this lecture today. So the first thing we're going to see is the hypothesis of continental drift. So in order to do that, I need to give you a little bit of a backup. So in the 1600s, there were better maps made by people, and this was done because of the discovery of America, partly, and the greater explorations around the world, of course. So better maps were made and were available. With these better maps, people started to realize that the continents sort of fit together as a jigsaw puzzle, especially if you put South America and Africa together, as you're seeing there on the picture on the right. So people gave little significance to this until about 1915, when Alfred Wegener, which is a German meteorologist, wrote The Origin of Continents and Oceans. So this book, which explained the hypothesis of continental drift, was very innovative, and it challenged the idea that continents and ocean basins were in fact not static, or it challenged the idea that they were static, and it presented an idea where these continents actually drifted their geographic location through time. So Alfred Wegener not only again challenged this idea that the continents and the ocean basins were static, but he, with the idea that continents drifted through time, also suggested that there had once existed a supercontinent consisting of all the Earth's land masses as we see them today. The supercontinent he called Pangaea. So Wegener hypothesized that Pangaea began to fragment into smaller pieces about 200 million years ago, which is in the Mesozoic era. And these pieces began to drift away from each other until they reached their current position as we know them today. So you're seeing there the image on the bottom left, the recreation of Pangaea as we think of it, and then below you see the drawing of Wegener as he kind of pictured how Pangaea was. So Wegener, like others before him, noticed the possibility for the continents to fit together as a jigsaw puzzle, as if once they had been together in reality. However, like others who also criticized his hypothesis, he noticed that the edges did not quite fit well together, as you can see in the image above from his redrawing of his book. You see that those edges of the continents don't quite fit together. So processes such as erosion would not make these edges fit together either. Erosion doesn't necessarily act that quickly for that all of that amount of material to simply disappear from the edges at that rate. However, scientists realized that there was a much better explanation of the two continents, South America and Africa, fitting together after they accounted for the continental shelves, which, as we saw in the last chapter, lie just submerged a few hundred feet or a few hundred meters, under the sea level. So if scientists account for the continental shelves to be the outer boundary of each continent, in fact, only a few areas had this missing or overlying material, as you're seeing there on the bottom picture. So this fit, which occurred until the 1960s, was much better than than what scientists had initially expected to see after accounting for those continental shelves. Okay, so in the next few slides, we'll go over the evidence that Wegener used for his continental drift hypothesis. So, although he did in fact start this hypothesis based on the continent's shapes, as we saw in the previous slide, it wasn't until he found out about the fossil correlation between different continents that he found this idea to be, or to have some substance in truth. So he provided the following lines of evidence for this hypothesis, and there's a few. So this first one is fossil matching across the seas. So he found out that some paleontologists had found fossils of the same organisms that were land-based organisms in different continents. So just as you see today, the fauna and flora differ in North America from Africa, from Australia. If the continents were separated before, then the fossils, which are the remains of previous species, should also differ between the different continents. But, as he pointed out by making reference to these three different species that you're seeing there, this was not the case. So one of those species is the Mesosaurus, which was a freshwater reptile and whose fossil remains limits the species to be to be of to be of Permian age. Permian age is about 260 million years old. So Mesosaurus fossils were only found in eastern South America and in western Africa, as you see in the image. So if the species had indeed made the long way across the Atlantic Ocean, its remains would be spread out a little bit more. If you think about it, if it had in fact traveled all through the Atlantic as we know it today, it probably wouldn't have landed in a perfect spot for the matching to be done as we're seeing it. It probably may have made it all the way down to parts of Patagonia or even parts of Guyana, not just perfectly as you're seeing it match there towards the middle of Brazil, right? So another species that he points out is Glossopteris, which is a seed fern. So Glossopteris has a tongue-shaped leaf and seeds that are too large to be carried by the wind. And it was found that this plant had once been widely dispersed throughout Africa, Australia, India, and South America. Later, fossil remains of Glossopteris were also found in Antarctica once enough exploration happened in that continent. So another cool thing about Glossopteris fossils was that Glossopteris was that they only grew in cold climate, unlike central Canada nowadays. So Wegener suggested that when these land masses were in fact together, they must have been located much closer to the South Pole, which was another interesting fact that later on proved to be probably right. A third fossil that he used was a third fossil that he used was the Lystrosaurus. So it was found in Africa, India, and later on in Antarctica, which is yet another species which was correlated through the different continents. In this specific one, your book doesn't have much detail, but it was still one that he used for correlation between those southern land masses. A second line of evidence that Wegener proposed for this continental drift hypothesis was that rock types and geologic features matched. So he found out that if he placed the continents together, certain features such as mountain chains or shields matched. And this was not just the type of rock, but also the amount of deformation that these rocks had experienced. So, for example, the highly deformed igneous province of Brazil and Guyana, which are over here, resembled rocks of the same type and age that are seen in Western Africa, right here. So you see those two shields pretty much match if you were to position them together, both in type of rock and in the formation of those rocks. Another example is a mountain belt that currently includes the Appalachians. So these mountains trend northeastward now and seem to disappear in Newfoundland, Canada, but the rocks correlate in age and type with the ones from the mountains in the British Isles and Scandinavia, and it was later found to even correlate with the ones in northwestern Africa and the Iberic Peninsula and in Greenland. So as you can see in the image on the top right, you see that matching. So top right, you see these Appalachians just kind of end in Newfoundland, Canada, but later on, they found that they correlated in age and type. So if you put them back together in the way that Wegener kind of proposed, it is suggested that these mountains formed in a nearly continuous belt.